Hi, today we'll be presenting about the design of the brake disc. The brake disc is a main component of the braking system in decelerating the vehicle to safety. When pressing on the pedal, the piston in the cylinder pressurizes the hydraulic fluid. This pushes a pad onto the rotor, and as a result, the vehicle's speed is reduced due to the friction between the brake pads and the brake disc. Here is a free body diagram of the disc brake, and we have selected the cast iron as a material for the disc brake due to being heat resistant and having a high toughness. So from knowing that our ultimate tensile strength for cast iron is 200 megapascal, our ideal endurance limit is 100 megapascal. And we've also considered the modifying factors. So for the surface factor, it is hot rolled, temperature factor at 600 degrees Celsius, and a reliability factor, we have assumed a 99% reliability. And for the miscellaneous factor, it is 1. So for multiplying the modifying factors by the ideal endurance limit, we have obtained a real endurance limit of 57.44 megapascal. Now as we head on to the static loading condition, we found out that axial and bending loads occur in a brake disc. We have made an assumption that there's a repeated load where the minimum stress is 0. And we found out the mean and alternating stress for bending and axial loads. Secondly, we obtained the mid-range and alternating von Mises stress for combined loading. Finally, we used a modified Goodman criterion to obtain the factor of safety of 8.1 for the disc brake. Next is the cyclic loading condition. So the necessary information that we know to solve this problem is the ultimate tensile strength and the completely reversed stress of 70 megapascal. So for the analysis, we found out that the fatigue strength fraction for cast iron was 0.9, and since the completely reversed stress of 70 megapascal is given, it would be equal to the fatigue strength. And from this computation, there would be 302,492 cycles.
Here's our static stress analysis. It has been given to loading conditions of 1.33 megapascals on the outer circular face, simulating the contact of the brake pads, and 600 newtons on the same face but in the radial direction to simulate the frictional forces. A rear view of the disc brake under those loads. This is our thermal analysis with set conditions of 600 degrees Celsius on the surfaces where the brake pads come in contact with the disc and 25 degrees Celsius on the other parts of the disc. 600 degrees Celsius is the operating temperature for a large number of disc brakes. Again, a rear view of the disc brake under those thermal loads. After doing the fatigue analysis, even at 300,000 cycles, there was no damage on the component. It was found that the disc brake had infinite life under those tested static loads.
Here's the final design for our disc brake. There's nothing out of the ordinary in comparison to the real-world designs of disc brakes. The difference, however, is that we consciously added more holes and placed fillets onto the edges where the caliper and disc are joined. The reason for the increased number of holes is that we want the temperature to decrease and dissipate faster, especially after every contact of the brake pad to the disc itself. In this way, longevity of the disc brake will improve, and more importantly, the performance of the vehicle will be enhanced. Here are the key dimensions of our assembly. These are the references used in the study. Thank you for listening on our short presentation. Have a good day.